This is your last lesson.
It is.
Well, he's gonna teach it to.
Oh, dang it is.
And sex, well, and sex, yeah.
Never mind. The last one for us.
All right. So I got ahead of myself, it looks like, Wednesday, and I did too much. So that will make it easier today. So I've been sneaking in every time when we did arithmetic and geometric sigma notation. But that's really what I wanted to talk about today, was just sigma notation. And sigma notation, we're not even talking about how to sum these. Although I might and just get a little bit ahead on Monday's work, make it a little bit easier on Monday, we'll see. But the key to sigma notation, and you already know this, is what goes right here to the right of this uppercase sigma.
Oh, it's
That would be the formula that finds the terms, right? So we call that the formula for the nth term. So if you were to find that Tn formula, whatever it is, not the Tn equals, but that part right there is what goes out there. And if it's got anything added to it, like you see in arithmetic sequences a lot of times, put it in parentheses, okay? Because if I were to write something like this, how do I know whether you mean to find the sum of all the terms by plugging a 1 in? And we'll talk more about what we do with these. See, if I plug a 1 in here, I get 2. I plug a 2, I get 4. I plug a 3, I get 6. So if I don't put parentheses around the 2n plus 5, it looks like I'm doing this. 2 plus 4 plus 6 all the way through 20. And then when I'm done, add 5. Does that make sense, what I'm saying? So you have to make sure to make that clear. If you want this to be part of your formula, put a parenthesis around it if there's a plus sign. It's understood that if there's a times sign, like 2 times 3 to the n, something like that, it's understood that you don't have to put a parenthesis around that. Does that make sense? So make sure that you do that. And at a math tournament, I remember them not putting parentheses around it, but they meant to. And because it was confusing. It's like, wait a minute, do I plug a 1 in here and get 7? Plug a 2 in and get 9? Do I do that all the way through 25? I plug in the 10 in? Or do I, if you don't have the parentheses, you don't know. Is that making sense what I'm saying? So basically with arithmetics, make sure you do that. Geometrics, you can if you want, but it's not necessary. Okay, so then what goes underneath the sigma notation? Okay, and the n has to match the variable here. So if you ever see one that has a j right there, then you'd have j's. Sometimes you see an I, and you'll have i's. In Algebra 2, we try to avoid i's there and there because people misinterpret that I as being an imaginary number. But whatever letter you see right here is the letter we use in our equation. I typically try to use n's this year. Typically, I'm not promising your book does that. And I might have forgotten occasionally on a worksheet or something. But once you get past this class, you'll see i's and j's and k's and l's, whatever. The letter doesn't matter. Are y'all with me? Okay, and then you see equals, and then what goes right here? The place of the what? Because it doesn't have to be 1. It's the place of the, and yeah, it'll be our first term. So I like to call it the initial term. The initial term in our series. And I'm going to call it a series because, again, we're adding stuff, right? It would be a sequence if there were commas. And then what goes in the numerator? I'm sorry, what goes above the sigma? What goes above the sigma?
How many terms?
No, not necessarily.
The last.
The what?
The last.
Exactly. It's the place of the last term. The place of the last one, the last term. So even though that n right there might not be a 1, it will be our initial term. And then all you do with these, again, the n in the equation is just the number you're plugging in, right? Like if I want to find the 5th term, the T5, I plug a 5 in. If I want to find the T100, I plug 100 in. So if I start with n equals this, I plug that in, and I'm going to go through every single term from here to there. I'm sorry, every single place from here to there, and I'm going to write all those terms out and put pluses in between. Except who really wants to do that, right? If I'm going from something like the 10th term to the 100th term, do you really think I want you to write all of them out? No. So what we do as a habit, if you do have a bunch of terms in there, and it's more than like 5 or 6 or whatever, if it's a really big number, it's a common habit when you write out your sequence to write out the first 3, put a dot, 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 another plus, and write the last one. And the reason why we do that is the first 3 will establish a what? A pattern. You can't see a pattern from 2, right? If I were to write 2 plus 6 plus, how do you know whether that's arithmetic, adding 4, or geometric times 3? Could be a quadratic, could be a harmonic, could be all kinds of different things. So I need to establish a pattern by writing out at least the first 3, and then plus, dot, 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 plus, and then whatever that last term is. Are y'all with me? Okay. Now, what does the sigma actually mean to you? Sigma. Sum. You're summing them up. Now, we're going to talk about that on Monday. Maybe we'll start today, but it won't be in your homework tonight. But the sum means you have to go and actually add them. If they ask you to add them tonight, then you're probably not going to have many terms, maybe 5 or 6 terms, and you'll be able to just go add them up. But if there was like 100 terms, we're going to have some formula to be able to add those arithmetic or geometric sums up. And we'll memorize those. We'll learn those on Monday. Again, maybe we'll dabble in it today. But anyway, so what we're going to focus on today are the kinds of questions you might see with an equation like this, or with an expression like this. So here is an example. The first question that you might be asked is expand the expression, expand the sigma notation. Maybe it'll just say expand, but look for that word expand. And expand, you might see something like this. N equals 5 to 20, 3n minus 4. So you'll see an expression, and it'll just say expand. Now, if you see that, they want you to literally write out what this means. So what does this mean? Well, that's the formula. So if I start with the 5th place, which is our initial term and ours, right? I guess we're skipping the first 4. Plug a 5 in, and I get 15 minus 4, which is 11. Sigma means sum. Then you go to the next place, plug a 6 in, you get 18 minus 4 is 14. Right? Put a plus, plug a 7 in, and I'm going to go through every place from 5 to 20. So there's 5, there's 6, there's 7, but because I really don't want to write all of them out, after 3, I'm going to go plus, dot, dot, plus, and I'm going to plug the last place in, which is 60 minus 4, which is 56. And this will establish the pattern, show me where I'm beginning and ending. And when you actually do go to find the sum on Monday, or maybe towards the end of the day, it shouldn't be a big deal actually using this information to plug in your formula. Are you with me? Okay, so that might be question 1, if you see this. The second question you might be asked is, how many terms are in this sequence? Sorry, in this series. Well, the hard way to do that is to write this out, and now you have you have a series, but you can treat it like a sequence, can you? And you know what kind of sequence is it? Arithmetic, And I know it's arithmetic because I can visibly see that I'm adding 3. I also know it's arithmetic because this looks like what kind of an equation? What? Linear. And linear expressions are arithmetic sequences. Why? Because you're rising a difference every time you run a term. So you can see I'm rising 3 for each term. So it's like rise 3, run 1, rise 3, run 1, rise 3, run 1. If I were to plot these like on a number line and say, okay, and you can start anywhere you want. You can start at the 5th term if you want. At the 5th term, I'm at 11. At the 6th term, I'm at 14. At the 7th term, I'm at 17. At the 8th term, I'm at 20. You see how it's forming a line? So it's a linear expression. So I can look at this and see linear right now and go, oh, it's arithmetic. And by the way, the common difference is 3. Because that's my rate of change. That's my slope, right? The rate at which this is changing is by 3s. Okay? But if I wanted to do it the hard way, I could look at this and go, well, since it's arithmetic, I do have a formula, don't I? And I could say, well, I've got a couple terms. Couldn't I plug 56 in here, right? And say 56 is in the I don't know what space. Are y'all with me? And I could say that 11 is in my what? I know it's in the, we use 5, but in this sequence, it's in the what? It's in my first place. I could do that, and my common difference is 3. And I could do the math on this and get 55. 45? Let's say 55 is not 55. I can get 45. I divide by 3 and I get 15. And I add 1 and I can see, oh yeah, I have 16 terms. But please don't do that. Because if it happens to be written in sigma notation, you can look at this right here. Right? This is a terrible waste of time to find out how many places if you have it in sigma notation. So think like this. How many places or how many terms would I have if I started with 1 and went through 20? That's easy, right? You have 20. Whenever I start in the first place and end in the 20th, I'm going to have 20, right? But if I start in the 5th, which ones did I leave off? The first 4? So could you just go 20 minus 4 and get that? But don't go 20 and don't go 20 minus 5 because I'm counting the 5th one. I've omitted, right? I've omitted 4 terms in this sequence, the first 4 technically. So I can just say 20 minus the 4 that were not included, and that's a much quicker way to get to that 16. Now, if I don't put it in sigma notation, and I give you just this, and I say how many terms, you have no choice, right? You're going to have to think this way. But I don't need that think that way if I'm in sigma notation. So the two things I could ask you, other than find the sum, are, if I give you this, are expand and how many terms. But if I don't say anything, like if you see this, and there is literally nothing said about this, right? And you just see that expression, what does this mean? Add them up. So if you see, and I would probably say find the sum or simplify or whatever, but literally when you see this, this means sum these terms, okay? So you would have to pull out your formula, where if it's arithmetic, pull out an arithmetic formula. If it's geometric, put out the geometric. If it's any one of the other weird ones we do, you'd have to use some other strategy. But we don't know that yet. Are you with me? So tonight you're going to see a whole lot of expand and a whole lot of how many, maybe a little bit of how many terms, that kind of stuff. All right, the other thing you're going to be asked to do is actually write it in sigma notation. So what if you had this? And the question is, if you saw that, it would mean what? That's all you saw. Add them up. And hopefully you would know a formula on test day, and you would go, oh, that's arithmetic. I'm adding 3. So if I'm adding 3, I'll pull out my arithmetic sum formula, which is on your little formula sheet, that hopefully you'll start memorizing either end of the day or maybe on Monday. And you memorize it, and you just plug stuff into that formula. It's not a big deal. And you might have to find some other piece of information to be able to do that. But tonight, if you saw that, you're probably not going to get asked the sum because we haven't talked about that yet. What you're going to be asked is to write in sigma notation or write using sigma notation. Okay? Which there's really no need to do this other than they're trying to give you practice with putting something in a different form. So what do you need for sigma notation? Other than a big, good-looking sigma? And if you stink at writing these, a little hint that almost solves all your problems, just make sure the top and the bottom are parallel. And then pretty much whatever you do with this, it ends up looking decent. Okay? The problem is when you don't make the top and the bottom parallel, you get a whole lot of that looking stuff. Okay? So if you just make these parallel, it's going to look pretty decent. All right? So what do I need with my sigma? So what's the formula here? Do you see a certain kind of expression? It's arithmetic. So you could pull out your Tn. And on your Tn formula, and why not use the T1 and the 1 formula? Because I can call that the first term. All right? So, and what did we say when we're finding a formula? What do I not want to plug in? Anything for Tn or n, right? I want to plug in everything else. Because the Tn and the n are like my x and y. So I don't want to plug anything for that if I want a formula, but I am going to eventually need to know what place that's in, right? But for now, Tn equals, and I know the first term is a 4, and I know the common difference is a 3, and I can certainly clean that up, and I get 3n plus 1. And that formula is what goes right here, and I want to put a plus in there to show, because it's arithmetic. I'm sorry, I want to put parentheses around there because there's a plus in the middle. Now what goes on the bottom? So the place of my first term, and what did I call my first term? 4, so n equals 1. And for the record, you're probably always going to do that. Doesn't mean the book's going to have that. I'll show you a second what the book might have as an answer, but your answer like this is fine. Okay? And then what goes there? A lot of people make this mistake. They put 319 there. It's the what? And it's not the number of terms. It's the, in this case it is, but it means what? The place of the last term. Now, the place of the last term, if you start with a 1, is the number of terms. But remember, there might be an equation that doesn't start with a 1, right? It might start with 10. Right? So how do I find the place of the 319?
319 minus 4 divided by 3.
And then plus 1. Or even better than that, why don't we just plug 319 in here? After I've used that and put it in there, I could just use it again and subtract a 1, divide by 3, and I get my 106. So as soon as I use that formula, then I can go back and reuse that by plugging it in there to solve for my n. Not too bad? And that's how you would write an arithmetic situation in sigma notation. And what happens if you have nothing there and it just says plus dot, dot, dot? Yeah, that just makes your life easy because you don't even have to do this part. You just come in here and completely ignore that part and just put an infinity up there. Not too bad? Okay, how about this? What if you have 5 minus 10 plus 20 minus dot, dot, dot. So I've got a 20. All the way through. That. And again, this would mean sum, find the sum, but tonight we're not going to do that. So this question tonight would be express or write using sigma notation. Okay, so what's the first thing you have to decide? Is it arithmetic or geometric, or in the future, maybe what is it, right? So I can look and see that this is what? Geometric, and if you can't readily see that, remember the check? If I go this minus this minus this, and I get the same thing, it's arithmetic. If if I go that over that, or that over that, excuse me, and I get the same thing, then it's geometric. And I do get the same thing, what do I get? -2 for my ratio. So what is my formula that I would have here? T1 times the ratio to the n minus 1 power. So what goes in my sigma notation expression? 5, yeah, -2 to the n minus 1. And then what goes on the bottom? If you're doing this, excuse me, n equals 1. And now what do I have to do? The place of that. Okay, well that, and how do I do that? Plug that in for Tn, so 20,480. I can divide by 5, which would give me 496. And we know what? 4096 is 2 to the 12. Would it also be -2 to the 12? And that would make sense here, wouldn't it? So at that point I can go, oh. And what if it wasn't 4096? What if it was 8192 or 16384? Some other higher power of 2 you didn't know. Remember, you know it's got to be a power of 2 because the only way for this to give me a whole number value of n is for it to be a power of 2, right? So you know it is. So if you did get a bigger number there that you didn't recognize, just divide it by 2's until you do recognize and then use that. Like if there were a couple extra 2's in there, I could divide them out until I saw 4096 and then go, oh yeah, that's a 2 to the 12 plus the other 2 2's, 2 to the 14. So you should be able to do that even if it's a little higher. But at this point, what do I see about how many terms? 13. Not a big deal? Okay. Lastly, maybe not lastly, but also, what happens if you see something like this? What do you see there? I'm adding 2 on the top. I'm multiplying the bottom by 4. Is that a sequence that we know of? It is not. But if the question said to express using sigma notation, could I still do it?
Yeah.
I could come up with basically a formula. I could just say, okay, well, it's got to be a fraction that spits out. And couldn't I put an arithmetic sequence on the top that stood for that? And then a geometric on the bottom that stood for that? That would make sense, wouldn't it? As long as it was spitting out the right fractions. So let's look at the arithmetic part. What would be my arithmetic? This is like my numerator. It looks like I'm adding 2, so my formula would go T1, which is 3, plus n minus 1 times the common difference. So wouldn't that give me a 2n plus 1? Does that work? If I plug a 1 in, do I get a 3? 2 in, do I get a 5? 3 in, I get a 7? So I could use that formula for the numerator. And then for the denominator, we said that was geometric. So I pull out my geometric formula. First term is 5. Ratio is 4 to the n minus 1. Right? I can put a 5 times 4 to the n minus 1 there. And go from n equals 1 to infinity. And if you're not sure it's working, check it. Plug a 1 in. Do you get 3/5? Yep. Plug a 2 in. Do you get 5/20? You seeing that? So you might see some stuff that's kind of odd looking. If you do, I can tell you this. There are some, I think, on the homework tonight that aren't arithmetic or geometric. They're trying to see if you can get creative. Like, everybody have this who wants it? Everybody? Okay. Like, what if I gave you this and said, write it using sigma notation? Okay. And you saw like, yeah. See it?
Oh, yeah, so we're gonna 3 plus 5 plus 7. So
How do I write a formula with that? You are right. Oh, it is a plus 3, plus 5, plus 7. If I'll just give you a little hint. If you ever see that the differences, the consecutive differences between terms look arithmetic, right? And arithmetic means linear, right? What's one higher power than linear? Now, exponential, for the record, I know what you're thinking. Exponential means the x is an exponent. Quadratic. If you see linear, this is linear, right? Mx plus b, ax plus b. Quadratic would have a squared in it. If you ever see that my differences are linear, then the equation representing this is quadratic. If you ever see that the differences are quadratic, the equation representing this would be cubic, one higher power. We're going to talk about that a lot more, and you won't have to worry about that so much on a test. The quadratic you will, but we'll spend a whole day doing quadratic, so you won't have to worry about that if we get to it, okay? So bottom line is, if it's quadratic, instead of thinking what something n plus something, think n squared. Think, what place squared? What would I have to do to make this work with the squared? I'll show you a better way than this guessing and checking. Will plugging a 1 in give me a 2? Will plugging a 2 in give me a 5? Will plug a 3 in give me a 9? Will plugging a 1 in give me a 2? Will plugging a 2 in give me a 5? 3 give me a 10? 4 give me a 17? So I'll show you a better way to do that as opposed to just random guessing. But at least if I'm noticing, wait, plus 3, plus 5, plus 7. If the differences are arithmetic, the formula's quadratic. It's just one higher power. Well, now that I know that, and I just say, oh, there's my sigma notation. What do I start with? 1. What do I end with? And you might see a couple of those tonight. If you do and you don't get them, don't worry about it. Okay? Because on my test, I tend to be a lot more straightforward. But they're just trying to give you random stuff tonight just to kind of see if you can figure it out. All right, now I'm going to throw you a little curveball. And this is a very common curveball. Everybody got this? Okay. Write this using sigma notation. Now, I know you see something, okay? What do you see in your own words? It seems like it's adding 3, but it's really not anywhere near adding 3. It kind of looks like if you forgot about the signs and made all the signs positive, you'd be adding 3, right? But then somehow the signs change. And that kind of feels geometric, doesn't it? Like you're multiplying by something negative each time. But you're not multiplying by something negative each time. But you can actually do this problem thinking about both those things, okay? So what I encourage you to do on these is the first thing is ignore the negative for a moment. Just forget about it, all right? So if I ignored the negative, so for the moment, if I ignore the negatives, I would have 4, 7, 10, 13, all the way through, right? And that wouldn't be a big deal. What's the formula for that? First term plus n minus 1 times 3. And my formula is 3n plus 1, isn't it? Yeah. Check it out. 3n plus 1. Now, will 3n plus 1 give me the 4, the 7, the 10, and the 13? I think so. So here's where I'm going to start. I'm going to put 4n plus 1. And that will give me 3n plus 1. Sorry. That will give me the 4. If I plug a 2 in there, that gives me the 7. A 3 in there, that gives me a 10. Now, you said that the negative reminded you of geometric, right? Because on geometric, when you multiply by a negative, it switched the signs. But I can't just go, oh, well, let's just multiply by a negative. Because if I just multiply by a negative, what happens? Everything switches. Now, if you think about it, on a geometric sequence, the negative would have been the ratio, wouldn't it? Like you would have done this on a geometric. You would have had your first term there. You would have had your ratio here, and it would have been raised to a power. And it was the power that switched the sign, didn't it? Right? Well, what if we just said times -1 to a power? Would that switch the sign? Yes. The problem is it might not switch it the way you want. Like, think about it right now. If I plug a 1 in there, I get 4. But if I plug a 1 in there, I get -1, and that would give me a -4. If I plug a 2 in there, I get 7. But if I plug a 2 in there, I get a +1. That gives me +7. So I'm swapping them the wrong ways, aren't I? So what's an easy, quick fix on that? I could either add or subtract 1 here. Most people do -1 because it kind of feels comfortable because it's kind of like our formula. And now what happens? You can do +1 though. Now if I plug a 1 in there, I get a 0. -1 to 0 is 1. But when I plug in there, I get the 4 that I want. And when I plug a 2 in there, I get a 7. But if I plug a 2 in there, I get a negative, which makes it the -7. And that alternates the sign. So if you ever want to alternate the sign, do the same thing you did with the geometric, except instead of plugging in a negative number, put a -1 and multiply it by that. And that allows you to alternate the sign when it's not geometric. When it's geometric, you could just use this, right? But it's not geometric. So we're not doing any of this other stuff. We're just borrowing this. And remember, if it starts negative, then I wouldn't want the -1, would I? If it starts negative, you can just leave that off. And again, just check it and see if it works for you. And then when you go home tonight and you're doing this problem and you feel really good about your answer and you see this and you're all excited and you go and look in the back of the book and they have this. Hold on. Are you going to freak out? No. You might look at your answer and go, what? Let me double check mine. But look, if I plug a 0 in there, don't I get 4? And if I plug a 0 in there, don't I get +1? And 1 times 4 is 4. And when I plug a 1 in there, don't I get 7? And a 1 in there gives me negative. They're just starting it with n equals 0. Which I don't know why they do that, but they do that on this key. You'll see it. I mentioned this a couple days ago thinking it was on the homework, but it's this homework that it does. So just remember, that's fine, but yours is great. My key probably looks like this, but I didn't make your book solutions. They're from the book. So just know that you very well may be right. Don't look at your answers and go, oh, I'm totally wrong. I don't know what I'm doing. Because it's probably not the case. You probably are fine. Well, I hope you're fine. Are you with me? Yes, no? Okay. Let me see if there's anything. What do I got? 1252. Great powers quiz, they would.
Yeah.
Let's do it.
We should do one, please.
All right, here's what I'm gonna do. I'm gonna make your life easier on Monday by starting something today, okay? And it'll stick in your brain. Hopefully when we go to Monday, it'll make it easier to get through Monday and then Tuesday and all those other, it'll be a nicer week next week. And since our test is on Friday, that'll kind of give us a little bit of flexibility. So I want to talk about the formula that we can use to add arithmetic sequences, okay? Now we can't add infinite arithmetic sequences. And the reason why we can't, if they go to infinity, in a lot of sequences we can't add. And if this doesn't make sense, it's okay, we'll come back to it later. But you can see, if I'm going to just write a very basic arithmetic sequence here. If this were to go forever, what is happening to my sum? It's increasing, but it's increasing towards a sum that approaches what? Infinity. Now, there are sums that increase in value, but don't approach infinity. And I'll mention this again, but like for instance, but they're not arithmetic. Like for instance, what if I was standing at this end of the room and say this room is 32 feet long, right? And let's just say I walked the first half of the room and that gave me 16 feet. And then I walked half of what was left. That would be what? Another, if it's total 32, another 8 feet, right? And that would get me over to about here. And then I walk another half of what's left, right? And what would that do? Add 4. And then I walk another half of what's left, which would be, and then another half of what's left, and then another half, and then another half. Now, my question to you is, am I still getting a bigger sum? Yeah, I'm still adding to it, right? I'm adding like right now it's 16, then it's 24, then it's 28, then it's 30, then it's 31, then it's 31 and a half, it's 31.75. I'm getting bigger, right? But the difference is my sum is not approaching infinity, is it? My sum is what we call converging on a number. It is converging on the 32. If your sum ever converges on a number, you can find the sum. If it doesn't, in the instance here, it's just getting bigger and bigger and bigger and bigger. We say that it is diverging. We are not going to be able to add the divergent sums. Not in this course, anyway. Now, you get some weird math, and there's all kinds of stuff that pops up, and you're like, what? I mean, some strange, like, literally, somebody brought in this in an alternate sum. And I'm like, what the heck? Like, not in this land, not in a master's degree, but in higher order doctorate level mathematics, there's a lot of stuff. Like, everything you learn in high school, everything you learn in college in a math degree, that's like the tip of the iceberg. There's a whole bunch of math below that that's just at another level. Okay? So we're going to talk about how to sum these. We can actually sum this. Okay? It does have a sum even though it's infinite. That bothers a lot of people. It's just kind of fun for me. But we'll get back to that later. But I cannot add sums of arithmetics. Right? Now, a long time ago, there was this little kid named Friedrich Gauss. All right? And Gauss actually went on to be a very famous mathematician. He did, when you solve systems and use the elimination method, okay, that's Gaussian elimination. He actually teamed up with this other guy, last name Jordan, I don't know much about him. But he's done a lot of different stuff with matrix theory, solving systems, all kinds of different branches. But I guess, you know how, like, if, you know, when you get older, you knew somebody when they were younger and they turned out to be this, like, a politician or a governor or a president or a famous basketball player or whatever, and you knew them when they were young, you had stories to tell about them. And I guess when Gauss was in first grade, his teacher said maybe to give the kids some practice adding, maybe because she wanted a little break. She said, I want everybody to add all the numbers between 1 and 100. Take some time, figure out what you can do. And before she could even sit down, young Friedrich said 5,050. Now, how did he do that so quickly? And especially when you keep in mind he was in first grade. Gauss noticed, yeah, like you're saying, he noticed that the outer pair, the second outer pair, the third outer pair, if you paired them up, you got the same answer every time, right? Every time I'm getting 101. So if you could only figure out how many pairs you have, you could just multiply the number of pairs by the outer sum. And even if there ended up being an odd number of terms, it wouldn't matter, because if there's an odd number of terms, then you have a half a pair, and that middle term is the same as the sum of a half of a pair. So he just said, well, find out how many pairs. And he said, well, if there's 100 terms, I could divide it by 2 to find out how many pairs I have. And to find the sum of these, I could just add the first and the last term. So we took that, multiplied it out, and got 505 with an extra 0. And it took him no time to get that answer, which is pretty impressive for a 6-year-old. Okay? And again, went on to do some really major things. But this right here is our formula, which I'm hoping, if you really think about it, now don't confuse that 100 there, because this 100, the one at the end, is different from that one at the beginning. And the reason why it is because sometimes that is not going to be the same as the number of terms, right? So you're going to want to know how many terms I have, and then you're going to want to use the first and the last term. It's just a coincidence in this problem that the last term and the number of terms were the same. So if you're ever adding a sequence like this, all you have to do, and it's arithmetic, got to make sure it's arithmetic, is know this formula. There's only one problem. Most arithmetic sequences, when I write them out, you don't know all 3 variables. Sorry, that's not a T2. That's a T what? TN. Make sure you get that right. So most of the time when you're given a problem, you don't know all 3 parts. So if you're missing a letter or a variable, what do you turn to figure it out? My other formula. So if I'm missing N, I turn to my other formula. If I'm missing Tn, I turn to my other formula to find it, and I'm home free. So for example, here we go. If I gave you 2 plus 5 plus 8 all the way through 311, I look at it and I go, plus 3 must be arithmetic. If it's arithmetic, I know that this sum formula is going to work. And all I have to know is the number of terms, the first term, and the last term. Now, the first term, 2. The last term, 311. What am I missing, though? So what do I turn to? The other formula. So I pull out my other formula, and I'm solving for n in it. So I plug 311 in for that term so that I can find its place. I plug 2 in for that term because I know its place, and I know the common difference is a 3. So I can subtract 2, divide by 3, add 1, carry that over, and at this point, all I got to do is take that 52 times that 313 and take a couple moments to multiply that out. And the other way you would see this problem, slightly different. The only difference is I could do this, and watch, it's not a whole lot different. Instead of giving you this plus 311, I could say something like this: sum the first 100 terms. Now, if I say sum the first 100 terms, still arithmetic, right? You with me? What's the difference? This time I know how many terms, which is like the place of the last term, right? But I don't know what? I don't know the last term. So in this situation, what do I turn to? The other formula, but I'm just finding this, right? This time I can go, oh, plug a 100 in, common difference is 3. I get 299 when I do that math, and I take that and plug it here. And if I were doing it, I would probably take the 301, well, I gotta cancel. Multiply it by 50. And again, get some from. That will not be on your work tonight. We'll revisit it on Monday. Y'all have a great weekend. And